Hey everybody, welcome back. We're going to start talking about the big daddy of all probability, or excuse me, of all statistics. And it is the normal probability distribution, or just the normal distribution. It is the bell-shaped curve. God, technology's great, isn't it? Look at this. I've got a bunch of bell-shaped curves over here, but let's go into this really easily. First and foremost, we need to talk about my normal curves end up looking, ooh, look at that. They end up looking like a boa constrictor that swallowed a goat. So you're going to have to bear with me for just a little bit. Remember, we've already talked about the normal or bell-shaped curve. We just haven't really given it a formal name yet. We know that the mean lives in the middle. Not only does the mean, but the median and the mode. It's symmetric. Okay, we know that the standard deviation, if I come out here where the curve is, if I go one standard deviation away from the mean, I pick up 68% of the data. So that guy right there is 68%. If I go one standard deviation away from the mean, if I go two standard deviations away from the mean, I pick up 95% of the data. And if I go three standard deviations away from the mean, I pick up 99.7% of all the data. Now, it's a probability distribution, and that really makes sense in context, because if you think about, like, really simply, if you think about IQs, well, I know that the mean, I know that the mean for IQs is 100, and that the standard deviation, excuse me, is 15. So we know that 100% of everybody has an IQ. So the probability that somebody has an IQ is 1, which means the sum of all of these probabilities has to sum up to 1. All right? Now, I'm going to give you the formula for it. It's actually, there's a function that describes this. You'll hear this sometimes written as a probability density function. You'll hear that in calculus. But there's actually a function that describes this here curve right here. And it's f of x equals 1 over sigma times the square root of 2 pi. It's the craziest looking function you've ever seen. E to the negative x minus mu squared divided by 2 sigma squared. All right, that's the formula for it. Okay, that's the formula for this curve. And we know that the area under the curve sums to 1. Now, let's stumble over here. Let's look at this bad boy right here, because this is actually really cool. What I have here is, I have what, 4 different probability distributions. Now, if you look at this thing, look at what's going on. What do we have? Let's look at the blue one first. The blue one has a mean, because it lives right here in the middle. We know that the mean is equal to 0, all right? And this tells me that the variance is equal to 0.2, all right? Now, if the variance is equal to 0.2, then I know that the square root of 0.2, excuse me, that the square root of 0.2 is 0.44. All right? Which means that all of the data, because the standard deviation is really small, it's packed in there really tightly. I guess it's 0.447, so let's include that. That means all of the data is crammed around the mean really closely. Now look at the red one. For the red one, ooh, I got colored pencil. I could have done that other one in blue. That would have been awesome. For the red guy, down here, I know that the mean is equal to 0 as well. Notice it's centered right here. And that the standard deviation is 1, because the variance is 1. Square root of 1 is 1. So the data is not as tightly packed around the mean. For the yellow one, I think I got a yellow one. Ooh, look at here. I love technology, man. For the yellow one, the mean is also 0. And the standard deviation, let's see, for yellow is equal to the square root of 5. I don't know that off the top of my head, but it's a little bigger than 2. Square root of 5, 2.23. 2.23, which means the data is way far away. However, the thing to realize here is that the area underneath this curve is exactly the same as the area underneath this curve is exactly the same as the area underneath this curve. They all add up to 1. They simply have different standard deviations. Now let's look at the green one here for just a sec. Here's my green guy. This guy also has all of the area, because remember, it's a normal curve. All that area, they all have the same area, adds up to 1. But this guy appears to have, let's see, if we absolutely had to guess, it appears that the mean is at negative, what, 2? Now, what do you think the standard deviation is? Well, when the standard deviation for the red one was 1, the standard deviation for the blue one was 0.447. I mean, if I had to guess, if somebody put a gun to my head in the park, I'd say, what, 0.6? You know, I don't know because I don't have the data in front of me. But I know that the mean is -2, and I know that the data is more tightly packed around -2 than the red one, and it's less tightly packed around -2 than the blue one was for both of these guys, by the way. That's around 0, of course. All right? So hopefully that'll give you a little bit of interesting information about normal probability distributions. Where it gets crazy is normal probability distributions. Think about it. What are examples of data that is normally distributed? In other words, the normal probability distribution describes its probabilities. All right. Well, we know for one, IQ, heights, weights. Why isn't that whites? Right. It's a strange thing. I never noticed that. IQ, heights, weights. In some cases, rates of growth, like the rate of growth of the grass. If I this would be a terrible job, but as a lab technician, if I had to go around and measure the growth rate of my grass, of each blade of grass. Now, clearly, I would in my backyard. I wouldn't measure them all. I would take samples from all over my yard, and what I would get is a normally distributed variable, which is really, really cool. One more thing notation-wise. Your author chooses not to observe kind of a standard convention of noting a normal distribution. And that's written like this. You always write it as n with the mean and the standard deviation. So if you were talking about IQs, it would be written as n with 115. If you were talking about, I don't know, the red one, this would be n with 0 and 1. Okay, so again, that's just a notational thing. So let's get back to playing around with some more normal distribution. All right, now here's the problem. If there are so many different variables that distribute themselves normally, in other words, there's so much data that looks like a normal curve, how can this be useful? You know, if, I don't know, the average lifespan of a freaking dung beetle on the Saharan desert. Do dung beetles live on the Saharan desert? I don't know. But let's assume that they do. And I'm trying to study them, and I'm trying to use one of these curves to figure out probabilities from. How am I going to find one of those? You know what I mean? Is there going to be a book that's got one of those curves published in it? Of course not. I would have to make it my own. So what we have, and this is the MoDaddy of all normal distributions. It is the standard normal. All right, the standard normal curve. And this is the granddaddy of all normal curves. And I'll show you the power of this in just a little bit, but not yet. Just be patient with me for a second. Distribution. All right. Now, the standard normal distribution has just the best mean and standard deviation ever. It's 0, 1. All right. So when I do this, like that, I know that this guy is 0, and I know that the standard deviation is 1. All right? It's called the standard normal because of this. I mean, we know where it's centered, and we know what its standard deviation is. And it really, which is to be demonstrated, excuse me, it's incredibly useful that we have this standard normal distribution, because I'm getting a little ahead of myself, so bear with me for a sec, but it's so powerful because, believe it or not, I can take any normal distribution and I can suck it down. I can distill it to the standard normal distribution. That looks like standard normal distribution. I can turn any normal distribution into the standard normal distribution by a really, really simple formula. But we'll get to that in just a little bit. Before we do anything further, I want to show you how to read probabilities off of this standard normal distribution. All right? So, but let's think about this for just a sec. They're not too, that one looks pretty bad. All right, think about this. I know that guy right there, oops, it's hard to dot with this thing. That guy right there is 0. We know the signal is 1. Now, unlike our probability distributions in the past, where our values had to do with discrete values. Remember, if I stumble back here to say the binomial, I mean, look at these. These are discrete values. This is 0, 1, 2, 3, 4, etc. Unlike those, the standard normal distribution has continuous variables. So if you think of these down here as the data values, then these are continuous. And then if I think about it here, like this area right here, this right here is the probability. That area down there. Because remember, the area of the whole, all of the area underneath the curve adds up to 1. It's a probability distribution. So this curve, in theory, is supposed to be spitting out probabilities. Okay? So, and we'll get into that here in just a sec. But let's play a little bit with a chart, and we'll see if you can start wrapping your brain around really the power of the standard normal distribution. Okay? Now I'm going to do something that's going to feel a little bit like a non sequitur. Okay? What if I wanted to figure out the probability of drawing a person at random with an IQ that is less than, say, 110? Let's really wrap our brain around what this means. Remember, IQs are normally distributed variable with a mean of 100 and a standard deviation of 15. All right? So really what I'm looking for here is it's got its own distribution. I know that the mean in the middle of this guy is 100, and if I go out, and this is horribly drawn, so bear with me, but let's say that that right there that's 100, then that's 115, because we're talking about one standard deviation away. So 110 is going to live about here. What we're really looking for, because this is a normally distributed variable, is we are looking for all of the area down here. Everything. Because the area, remember, of any, I know that the area underneath any curve, any normal curve, the area is equal to 1. Under the whole thing, I probably should have drawn that like that. Okay? Now, that is exactly the probability that we select a person at random with an IQ less than, or believe it or not, less than or equal to 110. Using this curve, it is impossible for us to figure out the probability of finding a person with an IQ exactly equal to 110, because I have to build out area. And any single value, let me change colors right here to illustrate this. Any single value has no area. It's got no width. So there's no way to measure its area. All right? So let's go back to the standard normal deviation, and let's talk, or standard normal distribution, and let's talk about how to find these areas. I'm jumping from an IQ normal distribution to the standard normal distribution, which is 0, 1. All right? Now, there are lots of ways to do this. The easiest way to do it is going to be to use your calculator, but even with your calculator, it can get a little bit tricky. All right, because it's difficult to program a calculator to get exactly what you want. Now, let's keep this simple, because we're going to need a little notation before we get crazy. All right, you ready? What we're going to do is, let's say, I'm going to call this value right here z. It's going to be a lowercase z. And what I'm going to do is I'm going to use a chart to figure out the probability that z is going to be less than some big Z, some number. This guy right here, don't worry about this. This is going to be just a number. And I'm going to use a table to do so. Now, again, I don't want you to get too wrapped up in the method by which we do this. You need to know how to do it, but what I really want you to do is start thinking in terms of how can I use this procedure that we're going to use to start applying it to things like finding the probability that somebody has an IQ that's less than 110. Okay? We're going to refer to this z-score from now on to be the data value on the standard normal distribution. So this is the data value on the standard normal. Standard normal. All right, you also hear this referred to as curve. So in this case, this guy right here, what we're going to do is we're going to turn down the road, we're going to turn this Z value, or excuse me, this 110 IQ into a Z value. Now, again, I'll explain how to do that down the road. Okay? So before we get too crazy, let's go back and let's look at a table. I'm going to show you how to do a table, or how to deal with a table here. And I just dragged this thing off of the internet. So check this out. Okay, look at this. So here's a normally distributed variable, all right? It's a standard normal curve. It says that right here, all right? There's a Z value. Now, what we're going to do is we're going to use this table. But I want to talk to you a little bit how this works first. It's telling us that the probability is this area or this region to the left of the Z value. By the way, this is the exact same type of chart that you have in your text. So if I have a Z value, that is negative 2.9. Now, what does that mean? Let's go back to my bamboo paper. Make this sucker big for a sec. All right, we're going to use that chart at negative 2.9, but we're going to hold off for a sec. Let's say, click over here to a new page. I can't believe I've done 60 pages worth of work. Remember, our Z value is the data value on the horizontal axis. So if this is 0, what negative 2.9 means, Z equals negative 2.9 really implies that I am 2.9 standard deviations, and that's really the key, to the left of 0, or of the mean. All right, so if I stumble over that, here's 0. I know that negative 1 is my first standard deviation. So negative 2, negative 2.9. What I'm looking for is the area to the left of that. So if I go back here to the internet and I go negative 2.90, and remember how this chart works, it gives me the area to the left of the Z value. Z value is just number of standard deviations away. The probability of laying to the left of negative 2.9 standard deviations is less than 1%. In fact, it's 19 out of 10,000. Okay? Now, I know I'm going to repeat myself a lot on this, so just bear with. What this really means is we have a probability of 0.0019 on the standard normal curve of getting a value below negative 2.9 standard deviations away from the mean on the left-hand side. Well, let's do one that's a little more reasonable. So let's go, I don't know, how about just negative 1.5. So if I'm trying to look, let's change colors. If I go Z equals negative 1.5, well now negative 1.5 is going to live right here. I'm looking for that area. All right. Now I'm going to start rewriting this. All right. I'm going to start rewriting this as the probability that Z is less than negative 1.5, because that's really what it is. I'm talking about less than negative 1.5. I stumble back over here. I'm going to try and find negative 1.5. Oh, there's negative 1.50. Negative 1.50 is right there. 0.0668. Think about it this way, ladies and gentlemen. 6.68% of all of the data in a normal curve lives below Z equals negative 1.5. Or the probability of grabbing a data value that is more than negative 1.5 standard deviations away from the mean on the left is 6.68%, or 0.0668. All right, how about this? What if I'm looking for this guy? Let me change my colored pencils again. Let's go back here. What if I'm looking for the probability that Z is greater than, say, negative 1.29? Now, this is going to take some thinking. But, okay, negative 1.29. You know what? I'm going to get bigger here, and I'm going to make a new curve. All right, so here we go. Now we're starting to look like that barracuda, or that anaconda that I said. So I'm looking for the probability that Z is greater than negative 1.29. So one standard deviation, we'll just call this just for giggles, z equals negative 1.29. But this time, I'm looking for the area to the right of that z-score. All right? I'm looking for all of that area. But Ripley, you dare say, our graph doesn't work that way. It only gives me values to the left. Well, let's see, negative 1.29. How do I do negative 1.29? Well, look at how my chart works. It gives me, here's negative 1.2, and if I stumble, whoops, if I stumble all the way over here, this value corresponds to negative 1.20, negative 1.21, negative 1.22, negative 1.23, get out of there, negative 1.23, etc. This value right here corresponds to the area to the left of z equals negative 1.29. So let's go back here and see if we can play with what that really means. I know that if this area, because my chart told me so, if this is 0.0985, the probability of being below negative 1.29, well, guess what the probability is of being above negative 1.29? It's one logical step that we have to make to figure it out. Well, I know that the area under the entire curve, because it's a probability distribution, the area under this thing is 1, so I simply go 1 minus 0.0985. That's that area, which is, what is that, 0.9015, is that right? And that's my answer, 0.9015. Isn't that cool? So it really doesn't matter how the chart looks. I'll show you another chart here in just a sec. But let's have fun with another one. I get in the habit, and I try to instill this in all my students, of drawing a curve every time I do it. I mean, look at my curves. They're horrific. Don't try not to have too much of an ego in this. What if I want the probability of z being greater than positive 1? Let's get away from 1. Let's go positive 0.38. Okay, 0.38. All right, so I'm going to draw myself just a little curve this time because you guys are probably getting tired of seeing that. Remember, it's on the standard normal, so 0 lives there. 0.38 is going to be pretty close to the mean, isn't it? It's not very many standard deviations away. It's going to be right there. Let's call it that right there. So that z equals 0.38, and I'm looking for the area above it. Okay, well, that doesn't seem too scary, except that my chart doesn't work that way. Oh, wait, and this chart doesn't even have positives on it. Okay, wait. Oh, well, looky here. That's kind of cool. Look at that. Now I've got z-scores that are above 0, which is nice. So between both pages, I've got everything I need. So all we got to do is go to z equals what did I say? 0.38, didn't I? Let me double check so I don't do anything silly. Yep, 0.38. So 0.3. I stumble over here to 0.08, so together they make 0.38. I think that's it right there, isn't it? So 0.38. I go back to my paper right here, and I know, again, let me change colors, I know that the area from 0.38 down, in other words, below 0.38, all of that area, this guy right here, according to that, is 0.648. So the area above, which is what I'm looking for, is 1 minus 0.648, which is what? 0.352. 352. And that, ladies and gentlemen, is my answer, which means the probability of finding something which is greater than 0.38 standard deviations away from the mean is 0.352. Now, your bunny ears are probably perking up. Ripley, it's weird when teachers talk about themselves in the third person, isn't it? Ripley says that any normal curve can be distilled down to the standard normal curve. All I need is a bridge. So if I think about, well, IQs, you've got a mean of 100 and a standard deviation of 15, but I can suck that distribution down into the standard normal curve, then all I need is this one curve to answer any and all questions that I have about any normal curve. I must say that one more time. If I have a bridge that can get me from any normal curve to the standard normal curve, This right here is the Rosetta Stone for all normal curves. It will get me anything that I want when I'm talking about normal curves. That's pretty powerful. I hope you see it for how powerful it is. If you don't now, you will shortly. All right, everybody. Just a couple more things about just the standard normal distribution, and then we'll start being able to have some real fun with this stuff. Okay? First things first, you might in your travels come across, like if you have a textbook that doesn't have the same chart as we have, sometimes charts look like this. Let me show you real quick. If I go, come on now, there we go. Watch this. Sometimes you'll have a chart that looks like this. Now look at this chart. What this chart is it says that the area between z equals 0 and this z value is what the chart is going to give you. So notice in this case what we have is all the z values from 0 to 3. So it just moves it from here to here. And you may say, well, Ripley, what about from 0 to -3 or -4? It's actually 3.99. But excuse me, what about -3.99? Well, remember, this is a symmetric curve. So whatever happens to the right is exactly the same as what happens to the left. So if I were going to use this chart with this, the way that this thing is designed, it's easy. I would simply, so let's go back and actually do one. So I'll put this thing over here. Let's say that I was trying to find the probability that z was less than 1.23. All right, so you know me. I'm going to draw myself a little curve. It's never a bad idea. And let's see, 1.23, we'll call that z equals 1.23. And I'm trying to find all this area in here. The problem is that this chart only gives me the area between z equals 0 and z, in this case, z equals 1.23, which we'll stumble over here to find in just a sec. But remember, this is a symmetric curve, and the area under the whole curve, I know that the area under the whole thing is always 1, which implies that all of this area here is half of 1, or is 0.5. So if I come over to my chart and I find 1.23, so here's 1.2, and then I go over to 3, I get 0.39065. So if I'm looking for all of this, this probability is equal to 0.5 plus, what did I say, 1.23 is 0.39065. We typically don't go out that far. Well, they went way far out there. So I'm just going to call this approximately equal to 0.89. Okay? So super simple. It's not difficult. You're just building out these little areas. All right? All right, let's get back into full screen mode here. Just one more topic, and then we'll move on to the next section, which is 6.3, which is really the uses of the z, which is, I promised you that we would figure out how this standard normal curve is the Rosetta Stone, and we're going to use the heck out of it. Excuse me, I had to wet my whistle. All right. One last piece of vocab. We are going to see in our travels, we're going to see z sub alpha. This is pronounced z sub alpha, or z alpha, you'll sometimes hear it referred to as. And what it is, excuse me, let's do implies. Alpha is just equal to the area to the right, and I'm going to do a little parenthetic thing here because I'll show you why, or left of the z value. And I'll show you what I mean. All right, watch this. If I do z sub 0.05, all right, now what that implies is this. Come over here with me real quick. Draw myself a normal curve. This is a standard normal curve, so I know here's 0. What we're saying is, what is the z-score? There's going to be a z sub 0.05 such that the area to the right of it is 0.05. Z sub, let me change colors here real quick, have a little fun. If I say, get out of there. If I say z sub 0.01, then that tells me, I draw myself a curve. They're all supposed to look the same, but as you can tell, they're not. Here's 0. Then over here, there is a z sub 0.01 such that the corresponding area to the right is 0.01. Well, let's play with our chart a little bit, because that's the reason that I wrote this little left thing right here. Remember, excuse me, there's this wonderful symmetric property about the standard about all normal curves. So do you see that whatever this z-score is, this z sub 0.01, there's going to be a corresponding negative z sub 0.01 over here, because there's going to be an area to the left over here, which is 0.01. Now that becomes really important when we try to use our chart. All right, so we go to our chart, and I'm going to try and find 0.05, or the closest thing to 0.05. So now remember, we're looking inside the body because these numbers in here correspond to the probability or the area underneath the curve. So I'm looking for 0.05, 0.0505, and 0.0495. Well, so I'm going to end up somewhere in between. So let's see, where does that get me? Negative 1.6, what is that? Negative 1.64, it's between negative 1.64 and negative 1.65. So when I stumble back over here onto my paper, remember, what the table's giving me right now is z equals negative 1.6. Now I'm going to split the difference and just say negative 1.645. However, remember, we want the z such that this alpha value to the right corresponds to the area. So it's easy. We have the symmetry property of the standard normal curve. So I know that this is equal to positive 1.645. See how that works? I only want, remember, this alpha value right there corresponds to the area underneath the curve, such that the z value chops it off. Now, just take a second. Try this one on your own. I'm going to take 3 deep breaths before I do it. Try to find z sub 0.01. So the z score that corresponds to the value such that the area to the right of that z score is equal to 0.01. All right, try it. Pause the video and try it yourself. Okay, hopefully you did what I said and paused the video and tried it for yourself. Let's stumble back into here. So I'm looking for 0.01. Now let's look at this. So here we go. Net 0.01, 0.0102, that's pretty close. 0.0099, ooh, that's even closer. I think I'm going to have to take this one because it's only 1/10,000th as opposed to 2/10,000th. So just to be sure, we're actually reducing it just a little bit, but we're going to call this negative 2.33. So I go back to my paper. I'm going to make it big. I go back to my paper, and remember, change colors again on this. I know that this score right here corresponds to z equals negative 2.33. However, I want the value to the right to be 0.01. So again, I just borrow the symmetric property of the standard normal curve, and I get z sub 0.01 equals positive 2.33. All right? And we're live. Hey, that's the end of the section. We're going to get lots and lots of practice on this chart, so I'm not expecting that you're going to know it straight off the bat. All right? We will play with this more tomorrow. We're going to jump into section 6.3 now in the next video, and we'll really start putting this thing to use. Okay? Thanks for your time and attention. Talk soon.